Okay, test. We'll see what we got for sound. Ooh, there it is. I hear it. Good. Test. All right, I'll turn the mic off. You can just leave the stream running. Okay, 8 o'clock. Live and running. Okay, welcome back, everybody. Last time we were talking about standing waves. So we determined that if you put boundaries on your waves and you say the wave has to go to 0 amplitude here and it has to go to 0 amplitude here over the length of a box, a one-dimensional box, length of a string we were talking about here, then that forced those 0 points at the end, that forced standing waves, the only waves that fit in the box, fit in those boundaries, were specific multiples of a half a wavelength. So we said these were the boundary conditions at 0 and at x equal L, so x equals 0, x equal L, the wave function psi had to be 0. And when we did that, we were able to say, well, what that looks like is a half a wavelength, a full wavelength, and 3 half a wavelengths. The waves that fit had half integer wavelengths. So I could say, just put n here, a number to count them up. So 1/2, 1 full wave, 3 halves, 1, 2, 3 is the value of n, and it's just an integer that counts up. So it's an integer value. It comes from the nature of the boundary conditions, and it starts at 1. We call that a quantum number. Now, when you get to here, this is all still just strings and waves. So this quantization comes simply from putting boundary conditions on something that behaves like a wave. So anything that behaves like a wave, water or strings, the common ones, that has this quantization. We don't normally think about it as quantization, but that is really all it is, even when we talk about matter and electrons. So the whole idea of quantum mechanics comes from a very, very simple concept that existed and was well understood way before anyone realized that matter behaves like waves. As soon as the experiments showed matter behaves like waves, there was that WTF moment when electrons, which we are understood to be matter, passed through a grating and gave an interference pattern. Electrons interfered with each other and gave you light and dark spots. We won't get into this. Matter gets quite a bit spookier than that. You probably say, okay, 1 electron through each slit or some stream of electrons through each slit. Sure, they could interfere with each other. They're waves. But you can turn down the electron beam intensity so that you're essentially getting 1 electron at a time hitting the grating. And even 1 at a time, the electrons still do that pattern. There's still high probability places they'll hit and low probability places they'll hit, 1 at a time. So this is an intrinsic feature of nature. And sure, we call it a wave and wave equations help, but there's something very fundamental about the nature of matter that even really goes beyond the description of just a wave. But wave mechanics describes it beautifully. So we'll keep using the math, and the math works. It predicts what happens, but we have to keep in mind on a fundamental level, nature, there's still a lot of mysteries in nature. It turns out you can mathematically describe the one at a time too. So don't be too shocked that we're just not going to go there. So what we have is a integer multiples of half wavelengths. We have the lowest energy state, which we're going to call the ground state. So low energy is ground state. And we can write lambda in terms of L. We wrote L in terms of lambda here. So it's absolutely fine to do that. And if we do write lambda in terms of L, we can substitute in lambda into our wave function. So we can write our wave function now x in terms, psi of x in terms of the quantum number, n, and the dimensions of the box, length of the box, L, and x, the running coordinate. So there's a one-dimensional wave, quantized. It has integer quantum numbers and integer energy levels. And that is the fundamental take-home. These are energies because they correspond to wavelengths or frequencies. And it was probably hard for you to tell, but when we did the rope experiment yesterday and we saw the standing waves, you could get this one. This is just jump rope. That's pretty easy. To get this one, you have to put a little bit more energy in. And to get this one, you're really putting a lot of energy in. So you can tell physically that that's a higher energy wave and a higher energy quantum state than this one. It's funny to call the notes on a violin quantum states. We don't usually do that, but they are all. That's all we are talking about here. If you take nothing else home from Chem 1, take home the fact that a wave property with boundaries naturally gives you quantization. It's a fundamental fact of nature, independent of the fact that matter sometimes behaves like waves. And we've already seen the de Broglie relationship. Matter only behaves like waves. The wave properties are only detectable for matter with tiny momenta. So they either have to have very, very, very small masses or be going very slowly. Small mass is usually sufficient for our circumstances, because we're talking about atoms and electrons in particular. So this could be either a string we're describing or a mass, an electron. So you arrive at the conclusion kind of quickly. If it was a physical bead on the string and it was zipping back and forth, it would have a kinetic energy, no potential energy. We're saying all this energy is kinetic, just moving back and forth. There's no up and down in the box. There's only the kinetic dimension. So it's all kinetic energy. It's moving back and forth, and it hits the end of the wall here, and immediately, no slowing down, immediately has velocity going in the other direction. So it has consistent kinetic energy about the whole length of the box. So if we say it with the wave we understood, with the particle, the question that might be in your mind is, well, where is the particle? And we're going to talk about that again. We can't tell now exactly where the particle is. All we can say is there's a probability of the particle being in certain parts of the box, and those probabilities aren't the same across the whole box. If they were the same across the whole box, that's kind of the classical. If it's zipping back and forth and any second you look at it, it's equally probable to be anywhere in the box. That is the real bead on a string. For electrons, something that's behaving truly like a wave, that's not the case. If you look at it and look away and look at it and look away, you'll see the more probable places that it exists, and that's different across the box. And we've already talked about it. That goes as the intensity of the wave function, the amplitude squared of the wave function. So if we square the wave function, that tells us, this one's easy because the square of this function looks a lot like this function. That tells us there's a higher probability of finding the electron near the center of the box than at the ends of the box. But it's smeared out over the whole box all the time. It only turns out that it exists at a certain point when you look at it. When you're not looking at it, it's all over the box. When you look at it, it's one place in the box, and the highest probability places are near the middle. There's another feature of quantum mechanics, and we're not going to get into that too deeply either, is when you measure it, it is in one spot or a region, in a probabilistic region. But if you don't, then it's all over the box as far as you know. So let's continue with this discussion. Let's see if we can do this ourselves. So we know boundaries on a wave give you quantization. So how about if we put the bead on a string and put the ends of the string together? So it's a bead on a loop. If we did that, what are the allowed wavelengths for a particle that's acting like a wave? What are the allowed wavelengths for a particle on a ring of radius r? So does it go, the wavelengths are 2 pi times n, 2 pi r divided by n, or n over 2 times the radius? What are the allowed wavelengths as a function of n, a quantum number? Has to be an integer. Think about that for a second, and we'll take a vote. That'll be captured. I'll give you this information up here, and if you'd like, go ahead and go to just this screen so you guys have relatively high res. And do we have a high res image of that? Okay, so you guys have a relatively high res image of some of the things that you might want to know here. Back on me. Talking to the director. Back on me. So a lot of you voted, so let's see what you're thinking here. Oh my goodness. Extremely popular. This is so extremely popular that I'm surprised. You're correct. B is correct, but this level of correctness on the first try, I'm surprised at. And I think, again, this is probably in the homework. So I think we'll try to limit the number of chem quizzes that make it into the homework per se, so you don't see them in advance. These are all over the internet now anyway. I made these a long time ago. But I would like it to be the first time you see it. But if for some percentage of you, you've seen it already, that's helpful because you can explain it to the other people in class. And you should be doing that, because let me emphasize, if you do a problem by yourself and you sit down and you get an answer and it agrees with the answer in the book or the correct answer, that's fine. And but it's not a measure of your understanding. Here's what it's a measure of your understanding. You explain that to someone. You say, here's why that answer is right. And here, and not just the mathematics, the steps you do to plug it in. Here's why that is right. Try to do that to somebody. And what you'll find is you'll get a step or two in and you'll go, oh crap, I don't really understand that. I don't really understand exactly why that's the case. And then you go back and you'll talk to each other or find a help from one of us, the teaching staff, or read some more or go out online. But the important thing is it identifies what you do not know. It identifies what you do not understand when you start to say it. And then start to say it. And when you can explain it to everyone, when you can move it from left brain to right brain, from your thoughtful part to your speaking part, that's all kinds of neural pathways that are making connections up there. And then you understand it, you learned it, and you'll remember it. And that's where I want everybody to get. I don't want you to be able to plug things into equations. You will. And everybody does for their first couple of years in science. But the goal is to understand underlying concept so that when you see other things, you understand them. So anyway, that was long-winded. This is correct. You guys were correct. B is the answer. Why is B the answer? Well, you can unwrap the circle. And the length, then it's just a one-dimensional problem. The length is 2 pi r. That's just the circumference of the circle. So what can fit in there? Well, one full wave fits. So why, though, does 1/2 a wave not work is the question. Why do half wavelengths don't work? So this was a solution when it was a string, but it's not now. Half wavelengths aren't going to work. And why is that? Well, if you have this half wavelength and you bring the string back together, then at the point where you bring it back together, these 2 points are coming down and going to 0, 1 point on the circle. And you can't continue around the circle in a continuous way. You have to go boink and then abruptly change directions and go this. It's not a smooth waveform. So that's not allowed. If you bring with the full wave, then when I'm leaving this end going up, and when I get back, I'm coming up. So it's a continuously distributed, and you continuously go along the wave with no abrupt changes. So the boundary conditions are slightly different, and this happens all the time in these quantum mechanical situations. Lambda is integer fractions, not half wavelengths. It's the boundary condition is that psi of x has to equal psi of x plus 2 pi. So that's going all the way around the circle, and the value has to be the same. Okay? That's important. You have to come to the same value. Not zero in this case, just the same value. The end can be anywhere on the circle. And though you have to have the condition that it's smoothly going up at those points or smoothly going down. So the second derivative, or excuse me, the first derivative, the slope at x and 2 pi away have to be the same too. So we bring this up because this is just a different set of boundary conditions, much too complicated to see on an exam or anything, but we can think it through here in class and get the idea that boundary conditions are not just 0 on this end, 0 on this end. Here it's the same value at each boundary and the same value of the first derivative, the same slope of the function. The slopes of the functions are going to be important. So we are going to talk about how curvy those lines are. The curviness is related to how energetic they are. Okay, so let's look at wave functions now in one dimension. We've kind of derived this, and we derived it very simply. We said it's a wave, and we saw what lambda was in terms of a quantum number and the dimension of the box. So we just solved a wave equation. We did some quantum mechanics. We just did it by inspection. You said, okay, it looks like one half wavelengths in half integer wavelengths fit. So here is our wave function. What does that mean? It resulted in a set of quantum numbers n, and for n equal 1, you have the wave function. And remember, it's a wave function. It's a standing wave, so it's oscillating up and down. It's like a plucked string. And when n equals 2, we put a full wavelength in the box. And when n equals 3, we fit 1.5 wavelengths in the box. And when n equals 4, we fit 2 full waves in the box. Okay? Now, so far we don't understand, we understand they're quantized, but we don't understand the distribution. We don't understand these spacings in the energy levels. And now I have to go back and emphasize, we're drawing an energy level diagram again. These are low energy, these are high energy. And remember, it's the spacing, the difference between them that matters. We can put 0 in energy anywhere we want. We could put 0 down here and 0 up here. The difference doesn't change. The difference in those spacings doesn't change regardless of where 0 is. That's the beauty of the state function of energy. But we have these, we don't know what the spacings are. And we don't know exactly where the particle is, but we've been saying, well, the intensity, the amplitude tells us is a measure of how many particles are there, the intensity. So if you take these and you square them, it looks like this. And what you see is these square functions tell you the regions where there's a higher probability, the regions of probability. So high probability of finding the particle in the middle, lower probability of finding it out at the edges. The particle's everywhere in the box. If you're not measuring it, you should think of it just smeared out, mass, just smeared, fuzzy, out of focus. When you look at it and you bring it into focus, it appears at one of these points. It can appear at any point in the box. It doesn't go to 0 probability till the end. But most likely, you'll see it here in the center. And then it gets funny because if it's higher energy, it's 0 probability of finding it in the middle of the box. So that's odd. It's an odd feature of the wave nature of matter. You go to higher energy, it becomes low probability to find it in the center. And then you continue up. The probabilities change and the probabilities change. One thing you might be noticing is you're getting as you go higher in energy, you're getting the particle spread out more in the box. Now it's more likely to be found all over the box because you have these high probabilities all over the box. It was behaving strangely at low energy where it was more commonly in the middle of the box, or even crazier, not found at all in the middle of the box. But going to higher energy is like going to higher momentum. And you know, as you go higher to higher momentum, those wavelengths get smaller and smaller and smaller, and you can kind of see that happening. And as those wavelengths get smaller and smaller and smaller, you start to lose your de Broglie wavelength. You start to lose the measurable wave characteristics. You start to become a particle that has an exact place. These particles don't have an exact place in space. So we count up these nodes. So nodes are a place where the wave function, the square of the wave function, basically where the wave function goes to 0. The square of 0 is still 0. So the wave function goes to 0 no times here. The ends don't count. Those are boundaries. But the wave function goes to 0 once in the middle of this wave function. It goes to 0 twice in the box. So that's 2 nodes here in this wave function and 3 nodes in this wave function. Nodes are a place of 0 probability. They're the weird part of wave, not just waves. We're not surprised when we see a trough in a wave, but a trough in matter, that surprises us. So the fact that the matter does not, we never, every time we measure it, we never get a measurement exactly in the middle of the box. We never see the particle in the middle of the box, is a little strange. Not strange for the wave itself or the string. Of course, it's vibrating. So the implications for matter are kind of funny. Notice that the nodes increase as the energy increases, and that's general. We'll take that home. If you take nothing else home from Chem 1, take home the fact that the more nodes in a wave function, the higher its energy. And that kind of also makes a little sense to us because more nodes means I'm crossing in between more, I'm crossing 0 more times. That's a higher energy wave. There's more curvature to the wave. Curvature and nodes give us high energy wave functions. So we could sort these out, and that sounds like a good exam question, doesn't it? I could give you these on a line, a straight line, and say you sort them out by energy, relative energy, and you would sort them out by the amount of curvature and number of nodes. So there you go. That's probably on the exam already. Your UGSIs, by the way, are so cool. They said yesterday, when is the exam going to be ready so we can read it? In general, it takes me a while to write the exam, mainly because I want to see what I emphasize and what I cover. But we need to get it done early so they can review it and there's no mistakes. And they're also saying to me, that's too hard. Back off. Let's do a easier question. So we are working for you already. They are working for you. Thank your teaching assistants. You guys are so lucky that you have this bunch this year. Now, what are the energies? We're not going to go through and derive this. I think in some of the reading that I clicked on that you can look at, they'll derive this energy levels for you. It's actually pretty simple. Simple. You use the boundary conditions on the wave function, and then you say things like, well, the particle has to be somewhere in the box. So I'll normalize the wave function and say the probability over the whole box is 1. And you can arrive with another assumption or two at this energy of each level. So this is the energy by n, the energy by quantum number, and of course it depends on n. In fact, it goes as n squared. That's rather surprising. And the length of the box squared. There's the mass of the particle and Planck's constant. So we can see the trends in energy. As n gets bigger, the energy gets bigger by the square of n. So here I've actually written it on scale. They weren't scaled before, but now they are. N equals 1 n equals 2 is 4 times the energy because the box and the mass aren't changing. So 4 times the energy, then n equals 3 is 9 times the energy of level 1. N equal 4 is 16 times the energy. And we could subtract that one from that one to find that energy difference. Just because I've written 1 down here doesn't mean 0 is right below it. What it means is those are the relative energy spacings. Whenever we draw an energy level diagram, the most important thing is the spacing, not where 0 is. Spacings between the energy levels. Turns out that's all we can measure in general. It's hard to get the exact energy of an energy level, but the differences are easy to get. So you can go through and also calculate what this amplitude is. We're not as concerned about that because 99% of the time we'll just draw a picture and say, where's the amplitude, big or small? And relative amplitudes is all we're interested in. But you can see the amplitude depends on the length of the box. And that might make sense to you because as you spread out, the box gets longer. You have to have, if it's the same mass, same number of particles or the same amount of mass has to be in that space, then the peak has to come down to spread out the mass over all that space. So there we go. Let's look at this situation now in a little more detail. So if you could switch to the board. So now you don't see me anymore. You just see this board. And what am I looking at? So you see a purple box here. See where this purple line is? And I'm going to drag the purple box down lower here. And then I'm going to drag the top of the box up higher. And now I've made something that really does look like a box. And what we're going to say is the potential energy. So the potential energy is 0 everywhere in the box. And the potential energy is ginormous. Mathematically, we can set it to infinity outside the box. So there's no way the particle can get out of the box because you can't give it infinite potential energy. It's trapped in the box. And this is the same thing we're going to do. And I think you're already anticipating this. When we talk about electrons, they're trapped in this kind of box with a plus charge down here. And they're trapped in this box. You can give them enough energy to get out. We know we can ionize them, but the shape of the box is different, but the idea is the same. The area of low potential energy here and very high potential energy out here, this time as a function of how far you are away from a center point. Okay? So we see that happening, and we're anticipating that already. But this is neat because you can play with it in real time. So what you have plotted down here, and I should use the annotation because you can't see me, what you have plotted down here is the wave function. And there it is. That's what we drew on the board. This is the lowest energy wave function. Now, importantly, that's not 0 in energy. The ground state is not 0 energy. There's some, when you put n equal 1 into that energy, you get a number. So the particle is never at rest. As low as you can get it, low a temperature, whatever you want to call it, the lowest energy you can cool that system to, the particle never stops. That's another part of the wave function of nature. We can't get that electron to rest. It's always moving. It's always a blur in space. So that's the lowest energy. And we can go up and we can just look at them. It's clever. So I can go to the second energy level. That's here. And you can see, oops, moving around, that is the 2 humps we saw. And you can keep going. There's the 3rd energy level, there's the 4th, and now we're looking at the square of the wave function. So a minute ago I just said it was psi. I'll correct that. It's hard to tell the difference in the ground state whether it's the square or the wave function because it's positive everywhere. So this is psi squared of x. That's the probability functions we're looking at. And you can see how those vary with the dimensions of the box. So I can take the box and I can make L bigger. And if I make L bigger, this would be a good chem quiz. What happens to the energy level? Well, there I go. I'm making the box bigger. What do I notice? Well, I notice that I have this same kind of pattern at this high energy. And if I go down to the first energy level, it still looks the same qualitatively. But look what's happening up. Look what's happening up here. The energy levels are much more tightly spaced together. And we know that energy has the property where it goes as n squared over L squared. So longer box, more tightly spaced energy levels. So I make the box big, the energy levels squeeze down, and it's now harder to detect it's quantized because the energy levels are closer together. And now you're going to say, oh, I see something else. If I make the box huge, infinitely long, the energy levels are going to get so tightly spaced together that there isn't quantization anymore. I can't detect energy levels. And that should make sense to you. I'm removing the boundary conditions. I'm letting the wave be everywhere. Fly, be free. Quantization goes away. Okay? That's beautiful. Let's see what it looks like. Let's see if we can look at the top energy level for this one. Ding. I think I can do some stuff here that I want to. I've overlapped 2 of them at once. Let me just go to one here. Let me go to a modest one. There is a modest one. I think I can, I can show the phase. And I want to do that because that sometimes confuses people. We're going to draw. Oh, let me turn that off and see if I can get. Don't have the resolution there. And I can barely see it here. I can't do that right now. Poop. That was a good exercise. Let me try this. Let me reload this. That'll take a second and see if I can get that to work. It's important enough, we'll wait for it. It does seem to be broken, darn it. I can't get any of those things to work. Okay. Oh, wait. Maybe I have to be, wave function has to be playing. Now it's playing. Now can I show the phase? Nope. Okay, sorry. What I wanted to show you, and I can just color, I can just do it myself. So when you look at the square of the wave function, you lose this information of whether the wave function itself was positive or negative in that region of space. So we call that the phase, and we often use it since if I'm looking at psi squared of x here, I don't know, was that a positive or a negative sign of the wave function? The wave function can go positive or negative. The square is always positive. So I don't know, was that one positive or negative? So we often do this. we shade them. So we'll color this one green to indicate that one was negative, and we'll shade them some other color, blue, to indicate that one was positive before I squared it. So that means this one would also have to be positive before I squared it. And this animation, when I was playing with earlier, did that automatically, but it's frozen now. But you're going to see that all the time. We're going to use color to indicate phase because the phase information goes away when you square it, and the phase information is important, and you'll probably be able to anticipate why before I even tell you. My computer's running really hot, so I'm worried that we're really stressing it out. So we've reached kind of a point here where we can say something about these waves. I've written this: delta x, delta p is about the size of Planck's constant. What I'm saying is the uncertainty in the position, delta x, and the uncertainty, the amount of spread in the momenta, the product of those is always a constant. So the spread, how spread you are out in space, goes inversely with how spread out your momenta are. So if you know the momenta and there's not very many values, the distribution of values is small, that's small, then the position uncertainty, we call it, the position spread gets big. Those things are inversely proportional. That's not reflected intensely here, except maybe in the ground state, where you say in the ground state position is not zero energy. If it went to zero energy, that would be zero momentum, and you would know the momentum exactly. So the spread in the momentum is zero. That means the spread in the space where the particle is spread out is infinite. There's no way to define where the particle is. So that's a conundrum. The particle must be somewhere. And this is a principle of quantum mechanics that says you can't do that. You have to have a balance between them. It's an annoying balance. If you try to squeeze in and see where the particle is, get to low spread in the position, then the spread and the momentum get crazy and you can't tell where it's going or how fast. So it's annoying from an experimental standpoint, but it's a fundamental property of just waves. It's not even a fundamental property of matter. Again, this is a property of just waves, but it applies to matter, and that's annoying to us for experimentalists. Okay, it's called the Heisenberg uncertainty principle. We'll touch on it a little bit as we go through our course here. So let's do this. Which bead on a string has the lowest ground state energy? So if I have an electron as my mass trapped in the box, or a hydrogen atom, or a neutron, which has the lowest ground state energy? Let's think about, let's talk through this one together, actually. We'll talk through this together and we'll see what you think. So which bead has the lowest energy? If I were to do this, you would say, well, it's a bead on a string. I know what the energy levels are. There go as the quantum number and the length of the box and the mass is in there. So the more massive you are, the lower, it's in the denominator, the lower your ground state energy is for every, and the lower your energy level is for every level, because M is just bigger. We already saw when L gets bigger, those energy levels dropped in energy and got more closely spaced. It's a squared effect. It's a quadratic effect for L. It's a linear effect in M. But that says higher mass, lower ground state energy. So which of these has the highest mass? Well, you can see electron, we know tiny mass, 1/2000th of a hydrogen atom. A hydrogen atom is just a proton, essentially. That's all the mass. It's in the nucleus. And that would actually be about the same mass as a neutron. So a proton and a neutron in the box would be kind of indistinguishable. They would have the same spread and distribution of energy levels because their mass is about the same. So let's look at that uncertainty principle thing again. And I just wanted to point out, you're not, I'm doing this mathematical part where I draw these pictures. You're not responsible for this math. The pictures are the important part. And what I'm emphasizing here is everything we've seen is just a property of a wave. Water or violin strings or any harmonics of the universe, anything you can describe as a wave does this stuff. It's not that matter is behaving differently than what we understand waves to do. It's the fact that it behaves like a wave in the first place is the crazy thing. So if I write a wave function, here's a wave function now just in terms of lambda again. So a generic wave function. And I look closely, well, what does that mean? If I have a single lambda, here I am, I have that standing wave going through all of space. I'm an unbound state. Let's say that it is bound to the size of the board. I haven't done that very well because I haven't had it go to 0 at both. Oh, we could have the 0 right there. Anyway, let's say it is bound in space just for shits, but it's a big space to deal with. So here is that lambda fitting in our box in space, but it's only one lambda. So de Broglie tells us that if I have a simple wavelength, I have a very well-defined momentum. So a single wavelength, there's the wavelength there, gives us a kind of a high level of certainty in the momenta because there's only one of them. What does that mean? Well, the square of this is the probability distribution, and you could see if you squared this, it would look like the probabilities was equal everywhere in the box. Low probability and equal everywhere. And in fact, even if this were a free particle, if you knew the momentum exactly of a free particle, you'd have no idea where it was. Uncertainty principle holds whether you're quantized or not. It's just always there bugging us. As long as you're a low enough energy to be a de Broglie, doesn't matter whether you're trapped or not, the uncertainty principle holds. So when you get to a certainty in momenta, there's less certain position. But remember how before I showed you that if you add up lots of different wavelengths and frequencies together, you can approximate any repeating function, any standing function. So if I add up many waves, I can get a function that looks like this. The sum looks like this. And that's just a property of waves. But that is uncertain momenta. You got millions of momenta. You don't know which one is the exact momenta. There's a huge spread. But look at what that does. That gives you a certainty, more certainty in where it is, a higher probability of it being right there. So this is the Fourier transform that I talked about before. You don't have to know too much about this, but I can show you this picture. So here is a Fourier transform. And here what we see on the board is a bunch of different wave functions added together. Okay? 9 of them. And when I add 9 of them together, I get this property here that I can define a particular value well in this region of space. So I have low uncertainty there because I have high uncertainty in I'm lighting up a bunch of different waves. And look, you can see that I can change how certain I am. If I just have one wave, then it's not very clear where I am in that region of space. It's spread out. But look, as I go to adding more and more and more waves together, how I get to a certainty in that. This is just a mathematical operation. It's the Fourier transform that I'm doing. It's transforming between time dimension and the frequency dimension. If you go between time and frequency, that's the same as going between energy and position. So these things hold. It's just a fundamental property of nature. And you probably understand this even better than that. You think this sounds weird to you, but what if you do this? What if you're at a stoplight and the car in front of you is turning left, and you come up, you're going to turn left, so you turn your blinker on. His is already flashing. You turn yours on and you started flashing. You might notice over a short period of time that it looks like you're flashing in unison. Blink, 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 blink. And you would say, I'm certain what his frequency is. Well, are you? So you're saying you have blink, blink, blink. And they were synchronized together. Well, actually, if you let it go for a longer time, so if you keep going and you gather more frequency information, blink, blink, you might see that, oh, I'm not really quite in sync. His frequency is different than mine. So that longer time dimension gave you more uncertainty in time, or a bigger spread of time, gave you a better understanding of his frequency because you watched for longer. That's all we're saying. Very simple expression. Watch a flashing light for longer, you're more certain what its frequency is. So frequency and time, delta frequency is a is an uncertainty principle. They're linked. So I think intuitively you understood it maybe better than you thought. You just had to have somebody tell you. And that's what I'm here to do. Okay. So this is called the uncertainty principle, and we'll write it down. The spread of values in X and the spread in values of momenta or energy. Remember, if all you have is kinetic energy of motion, then all your energy is kinetic, then you can express that in terms of just the momentum. So your energy is expressed by your momentum, because momentum is m times v, and kinetic energy is 1/2 mv squared. So those things are locked together if you have only kinetic energy. And that's what we have in these boxes. We say no potential energy at all. Okay, well, let me see if you understand that then. What's the result of narrowing this slit? So I have a wave or a particle, whatever the heck you want to call it, impingent on just one slit now. So diffraction is all that matters. There's no interference. The question is, if I narrow the slit, what is the result? So let's talk about that. And we'll take a vote. Okay, I had a great discussion in my breakout room. Let's see what you guys are thinking. Many of our are thinking A, a few of us are thinking C. B was the option where it didn't change much. I think a lot of people are saying, well, it probably changed. A is squeezing together, getting narrower. So we open the slit. Did I say open the slit? I forget what I said. I narrow the slit. So narrow the slit. So you're saying I narrow the slit and I get a narrower distribution. And indeed, that is what would happen if it were actually just BBs. If you were shooting like a BB gun, you would go flying through that slit, and sometimes you'd hit the edge of the slit, so you'd spread out a little bit. But if you narrowed it, you'd have a narrower distribution of your BB gun or your whatever pea shooter. If it were Einstein, totally pea shooter. But for a quantum particle, a particle that's behaving like a wave or any wave, if it was just light, what does it mean if you decrease the slit? The animation doesn't look like it's doing what I want here. Oh, there I go. I decrease the slit. So here I have a wide slit, and here I decrease, I make it narrower. If it's narrower, I know now better what the position is in that dimension. There are fewer possible positions in that dimension. So I know it better. The spread in that dimension got smaller. That means the momentum in that position, in that direction, got bigger. The spread, not magnitude. I didn't mean to say magnitude. The spread in values got bigger. And if the spread in values gets bigger, that means I could have many more velocities, since it's a momentum, many more velocities. So by the time I get from here to here, there's many more opportunities to spread out if I make that more narrow. So counterintuitively, the diffraction pattern gets more broad for a particle behaving like a wave. Okay, delta x got smaller, delta p got bigger, and we increase the uncertainty in the x momentum. Here's a bigger delta p, different velocities in that direction, and c is the way to go here. And we actually saw this. We showed it last time. If you can go to the screen, Sydney. We showed this last time. How's the resolution? Is it good? Good. We showed this. We talked mostly about the interference. And interference by itself is just the waves interfering, and I'm getting bright and dark spots. Diffraction by itself is the spread of possible values. It's the imaging of these slits. And I can change that. There I'm making the slits bigger. You can see I'm making the slits bigger. My image is getting smaller. Here I'll make my slits smaller, and I can't tell where the particles' momenta are anymore. Okay? So it's a fact of life, and we saw it. We can put the interference pattern back on there and overlap them. So so you get this kind of pattern, diffraction and interference adding together, a broader range of positions, but still interfering with each other as waves. All right, that's lovely. Okay, so let's do an absorption of energy now. Which absorption, so going from N1 to 2, so these are the various n values from 1 to 2, from 2 to 3, or from 3 to 1, which absorption requires the highest energy? And the energy could come from a single photon, but just the highest energy in general. How much energy do I have to absorb to do these things? So I'll start the counter, start your quiz counter, talk about that amongst yourselves, and we'll take a vote. You can show them the screen on this. You guys have all these slides, so I guess I don't have to do this for you, but there's the information that you might need to do this. Okay, let's come back together here. We had a very useful discussion there, and we're a little spread out here. A third for B, but essentially 2/3 for the other two. So let's see what, let me give you my thinking on this. So we have to go back to the energy expression. The change in energy is the final state minus the initial state. So final state is the second state, initial state, the first state. So N2 minus N1. The question is, what are the values of N2 and 1? Is N2 2 to 1, or 3 to 2, or 1 to 3? So you can put all those various values in there. And here I just drew them. I didn't draw it to scale. I just drew 3 energy levels. You really can't scale it until you know M and L. So just generic 3 boxes, they don't take this spread in energies till you know the mass and the length of the box. So you kind of need those. Don't show you them there. But once you fix M and L, we saw the spread. We saw how they went. They go as the square of N. So going as the square of N gives you this spacing. And here you can see already, you don't even have to do any math. The 2 to 3 transition is bigger than the 1 to 2 transition. The other transition we talked about was 3 to 1, and that was the biggest, but that's an emission. That's energy comes out, is released when I do that. We were talking about absorbing energy. So we can see it straight away with a picture. We don't have to do the math. We could do the math, and we could put those numbers in there and get exactly what delta E is. 2 to 3, the biggest. So that brings us to just generic absorption and emission. And we already talked about it, but we saw that absorption and emission could happen in this continuous way, where you have a broad range of absorptions or emissions, or this discrete way where you absorb exactly one frequency or emit exactly one frequency. So now I think you understand why that is. So if you have a system with electrons that are trapped in boxes, then they will have these allowed energy levels. And the allowed energy levels the spacing between them determines what's absorbed and what's emitted. And it's an interesting fact of nature, the reason why so many things are colored, for instance, that these spacings, the delta E, happens to be in energies that are around the visible region. So the spectrometer that we need, piece of instrumentation we need, is our eyeball sometimes. We can see absorptions and emissions. We saw that. If you absorb all the blues, you look red. I can tell you're absorbing blues because I'm detecting the reds. So I can do that simple spectroscopy experiment. When it's individual frequencies, when it's discrete, we need a piece of instrumentation to spread out the frequencies so we can read them individually. And you can do that with a Fourier transform. Take all the wavelengths, take the Fourier transforms, and you get the exact frequencies that are in there. Don't got to know that unless you're going to be a chemist. Please, some of you who are being a chemist, that's actually what we do. We measure all the frequencies together, and it's a mess. It's a bright light. We do the Fourier transform, and that gives us the exact frequencies. It's cool. Anyhow, these are in the visible region. These spacings are in the visible region. And not just in the visible region. Electronic transitions happen in a broad range, but fortunately, some of them in the visible range. So what does that mean? That means electronic transitions, electrons moving between these energy levels. A photon, here's a photon, high energy photon of maybe nearly ultraviolet light. It's purple. That will impinge on our system, our molecules, with electrons. Is it absorbed? Well, I don't know. It's absorbed only if there is an appropriate spacing that's that size, that has that energy. And that one wasn't absorbed. It blasted right through. So here's a slightly lower energy photon, longer wavelength, and I've drawn it more bluish. That one gets to the system, and there is a spacing that has h nu. Its delta E is h nu. That one is absorbed. So an electron goes from this energy level to that energy level, absorbs that photon. We're standing over here. It didn't get to us. We didn't see that photon. So some blues are being removed, and what's hitting us is what the color that we see. Or we could have a fancy spectrometer and we could measure exactly the frequency, so that absorption frequency would remove that frequency from the continuous range of colors. There's a green, turns out there's a good green spacing. And here comes a yellow. Oop, there wasn't a good yellow. So over here, we're seeing the yellows and those violets coming through. That's making some color over here for us. Here's a reddish one. That reddish one is also absorbed. So that is taken from the continuous spectrum. So I see, if I'm standing over here and I'm shining light, I see all these colors except the ones that were absorbed. And since they're single frequencies, I might not even be able to tell. I might just still see the white light, all colors, because they're just those individual specific 3 frequencies. If I do the experiment more cleverly, I excite the system and let those photons come out. So let the electrons drop down, the emission experiment. Then I can have a detector and I can be standing over here and there's no white light anymore. I excited this and now I see just the photons coming out. And if I have a little grating that I can separate the frequencies, I can see, oh, a red photon, a very specific one, comes out, very specific energy. So now I'm plotting energy here, higher energy going that way, apparently. Here's green. That's a higher energy photon. I see that. That hits me in the eyeball. And the blue one can also emit. So if I can get this system artificially to a high energy state, and you can do that, you don't have to use light, you can excite it some other way, heat, electric current, and then watch it relax back to ground state. Excited state to ground state. It's called relaxation. I guess that that should be obvious. That's why we call it relaxation. You would see those 3 frequencies. If you saw them all together, it might look yellowish because of the combination of them. But if you separated them with a special piece of equipment, you could see the individual lines. And we saw Lonnie did that. Remember, he took the mercury vapor lamp. So we were heating up mercury atoms with electric current. The light coming out looked white because it was this combination. It was very bright. But if we looked carefully, we could separate into 3 distinct frequencies. And this now we understand is why. There's some bound electrons in there. They have individual energy levels, and we're having transitions between them. And those are discrete packages, delta E. And if they're equal to a photon, we'll detect that photon energy coming out. Okay, let's go through this one. Let's go through this one together, I think. And then we'll talk about one to end on. So here's the energy level scheme and the emission spectrum. So here's some generic energy level scheme coming from some bound state of matter, some bound electrons. We don't know the masses, we don't know the lengths of the boxes, we don't know anything, but here's what it ends up being. A little different than what we've seen so far. The energy levels, well, not not tremendously different. So here is our energy level scheme. Higher energy, all I care about is the differences in energy. Here is the emission spectrum. So here are the frequencies that are emitted. One at A, one at B, one at C. So, and now be careful. Here I've drawn increasing wavelength going that way. So increasing frequency going this way. So if wavelength is going that way, this is not higher energy. This is lower energy over here. Energy goes as the frequency inverse as the wavelength. So the way I've drawn this picture, and be careful when you're reading these diagrams, make sure you know what the axis is. So C is a low energy emission. B and A are slightly higher energy emissions. The question is, what is the question? Which line arises from 3 to 1? So I need you to tell me this is the transition. Is that line A, B, or C? Well, 3 to 1 is the highest possible emission energy from that. There's a bunch of them, right? You go 3 to 2 here. But that's the highest. So you'd expect to see that at the highest, and that's A, because I'm down here at high frequency, low wavelength. But you can see the other two there, right? There's the high energy one, emission here. Here is the another one that's pretty high energy here. And then you have a little bitty one here, much lower. So these are pretty close in energy, A and B, but C, small amount of energy. So there's the 3 photons emitted, specific frequencies or wavelengths, and we can identify all the transitions and all the lines in the spectrum. I probably do that here. I didn't have to draw the picture. There they are, A, B, and C. It's fun if I do it in real time too. I would do everything in real time, except you can see that my handwriting is just a wreck. So to which energy level scheme, let's do this one together. I mean, let's do this one as a chem quiz. Talk about this in your groups. Which energy level scheme? So here's 3 energy level schemes. I have, oops, sorry. Oh, for goodness sake. Oh, now I've broken it. Okay. Sorry, the computer is, I pushed the buttons too fast and it's too tired for that. So I just wanted to put energy going up on the board there. 3 energy level schemes. Here's the spectrum, the distribution of frequencies you get from that. Which of these corresponds to that? Think about that for a second, and we'll take a vote. Okay. So let's come back together. We just have a few minutes for me to explain this one for you. Let's see what you're thinking. Many of us, well over half of us think A is this energy level scheme corresponds to that spectrum. So the A people are thinking you take this, you can actually do that. You take this you're saying you take this and you flip it on its side and you get that spectrum there. Maybe that's what you're thinking. I don't know. That's certainly one way to think about that. So is that actually the case? So what you have to do is you have to draw out all the possibilities. Here I've drawn out the possibilities for you. Draw all the possible transitions and be organized. So what I want to do here is draw all the possible transitions. So go from highest to lowest, and then next highest to lowest, and then next highest to lowest. That's 3 of high energy, but then you have to go highest to second lowest, and then this guy and this guy. Those are all possible transitions. Now, that would look like this: 3 high energy, but 2 low energy. I've got 3 lines, but these 2 are the same size. So they're right on top of each other. So that's not exactly the same. In fact, you have to look at this one. Here I have a very high, and then these 2, this guy going to here and this guy going to here, are not as big, but they're the same size because of the relative spacings. And then this guy also relatively high, but slightly lower than the other 2. So that's those 3. And then this transition and this transition also possible, but the same size. So that's that one. So the answer here is B. Fantastic. Play with those. That's a favorite exam question. Tells you understand emissions and you can order them and their relative sizes, and it's a picture. You can tell what I like, right? It's a picture. You don't have to do any math, but you understood what's going on, and you could go, oh, these are energies arranged here. These are energy spacings. So I have an energy distribution here. I have energy spacings here. A beautiful mapping from the energetics to the spectrum. And we will see you tomorrow.